give an important definition. So omega in Rn open set, f from omega to r measurable. We say that f is locally integrable on omega, and the notation for that is f belongs to L1 log of omega. Okay, if integral over k mod f dx is finite for every k contained in omega compact. Okay, so if it's integrable on every compact subset, then you say it is locally integrable. So examples. So f in L1 of omega automatically implies that f is locally integrable. F in any LP of omega 1 less than p less than or equal to infinity, then also f is locally integrable. Because if it is LP on if it's L infinity, it's a bounded function, and bounded function is always integrable on any compact set because compact sets have finite measure. And if it's in LP, then it's LP in any compact set also, and if it's LP in a compact sets have finite measure. We have seen that it is L1 in a compact measure. Okay, then if f is continuous, f continuous implies that f is locally compact, locally integrable, because here also it is bounded, and therefore any continuous function on a compact set is bounded, and therefore it is locally integrable. Let me give one more example of a locally integrable function, which is an unbounded function and which does not come really in any of these categories. So let us take omega equal to the ball, center origin, radius 1, okay, and contained in R2. Okay, and then you take f of x equals 1 by mod x if x is not 0. So this function is defined only outside the origin. It's defined almost everywhere. It's not defined at one point which has measure 0, and it is unbounded. So because as you go near 0, this becomes bigger and bigger. It becomes almost 0, and therefore the function blows up near the origin. We want to show that f is locally integral. So f belongs to L1 log of omega. So we have the unit ball. Okay, now if k is any compact set which does not contain the origin, then of course it's okay, because that's there the function is a continuous function, therefore it is bounded, and therefore it's integrable. So we only have to look at neighborhoods of the origin where f is unbounded, and therefore we have to check if it's locally integrable. So enough to check on B closure 0 epsilon small and greater than or equal to 0. So this is a closure. So closed ball, that's a compact set which contains the origin, and any other compact set near the containing the origin can be put inside ball. So in fact epsilon small is really not necessary. Epsilon greater than 0 is fine. Okay, so it's enough to check this. So let us integrate this. So B closure 0 epsilon mod f dx, and that's equal to integral 1 by x B closure 0 epsilon, and I'm going to use polar coordinates. So this is equal to 0 to epsilon integral 0 to 2 pi. So you have r dr d theta, that is what dx dx1 dx2 which is dx will become, and then you have to put 1 by r, and the beauty is that this r gets cancelled, so you just get 2 pi times epsilon, which is always finite. Okay, so this is a function which is unbounded and which is locally integrable. So now we have the following proposition which will be useful for us in the future. So let f belong to L1 loc of omega, so it's locally integrable, be such that integral over omega fg dx equal to 0 for all g in Cc of omega. So omega in Rn open set. Okay, then f equal to 0 almost everywhere. Okay, so this in omega. So this is, if a function, when you integrate it, multiply by any C infinity, is a continuous function with compact support, and integrate, if you get 0 as the integral, then the function in fact has to be 0. So we will prove this in some few steps. So step 1. So you assume f is integrable on omega, that is f belongs not to L1 loc but to L1 of omega. So that is, as I said, an example of a locally integrable function, and mod omega is finite. So let us assume both these properties. Then there exists f1 belong to Cc of omega such that norm f, so let epsilon be greater than 0, f minus f1 in L1 is less than epsilon, because Cc of omega is dense in L1. Okay, so then integral of omega modulus f1g dx is mod integral over omega f1 minus f times g dx, because integral fg dx is 0, so I have just subtracted 0, and that is less than or equal to epsilon times norm g infinity, because the norm L1 norm is less than epsilon, and that is less than this. So now you define, let k1 be the set of all x in omega such that f1x is greater than equal to epsilon, and k2 equals set of all x in omega such that f1 of x is less than or equal to minus epsilon. So both of these sets are closed. Okay, and k equals k1 union k2. Okay, and they are closed subsets, and this is compact because f1 has compact support. So this is compact since f1 has compact support. And then k1 intersection k2 is empty. Okay, so we have two disjoint closed sets, and therefore we can use Eurizon's lemma from topology. Implies there exists a h which is in Cc of omega such that h is identically 1 on k1 and h is identically 1 on k2, minus 1 on k2, and also such that mod hx is less than or equal to 1 for all x in omega. In fact, it can be taken between minus 1 and 1. That's what we exactly are saying. Okay, so now if you have such a h, okay, so you have integral on omega f1 of h dx equals integral omega minus k f1 of h dx plus integral over k f1 of h dx. I am just splitting the integral. Now integral so you have integral of what is on k. K is h is plus 1 on k1 minus 1 on k2, and therefore if you multiply on k1 it is non-negative, k2 it is negative, and therefore if you multiply you will get mod f1 on k. That is this term. This term is equal to that. Is dx equals integral f1h on k dx, and that is less than or equal to f1 of h dx is less than epsilon times norm h. That is what we just saw. Where did we see that? f1g is epsilon times norm g for any seen function with compact support. So this is less than epsilon times norm h infinity is 1, and then plus the other term integral of omega minus k of mod f1h dx, and that is less than or equal to epsilon plus integral on omega minus k. Mod h is again less than or equal to 1, so mod f1 dx. Okay. Therefore, but what happens on omega minus k? On omega minus k, mod f1 of x is less than or equal to epsilon, because on what are k1 and k2, that's where it is bigger than epsilon, so here it has to be less than epsilon. Therefore, integral on omega of mod f1 dx is integral on omega integral on k mod f1 dx plus integral on omega minus k mod f1 dx. Integral on k mod f1 we have already seen, this is less than or equal to epsilon plus integral on omega minus k, so 2 times integral over omega minus k mod f1 dx, and on omega minus k mod f1 is less than epsilon, so this is equal to epsilon plus 2 epsilon times measure of mod omega minus k, and I can make that less than measure of mod omega, so there is no problem, that is finite. You have this. So norm of f in L1 is less than or equal to norm of f minus f1 in L1 plus norm of f1 in L1 and f1, and that is equal, f minus f1 is less than epsilon, norm of f1 we have just computed, it is also less than epsilon plus 2 epsilon mod omega, so this is less than or equal to 2 epsilon or equal to 2 epsilon times 1 plus mod omega, which can be made arbitrarily small, and therefore this implies that f equal to 0. Okay, so that is the first step where we assume. So now step 2, general case. So you write again omega u equals union omega n, n equals 1 to infinity, omega n is omega intersection b0 n. Then you know that omega n closure is compact. So f is locally integrable, therefore f belongs to, f restricted to omega n belongs to L1 of omega n. Okay, and further mod omega n, which is the measure, is also finite because it is contained in a ball, and therefore by the previous, by step 1 we have that f restricted to omega n equals 0 almost everywhere on omega n. So there is a set En of 0 measure, except on that f restricted to omega n is 0. So then if you take f equal to 0 almost everywhere on omega, because you have the only sets where it's not 0 are the ENs which have measure 0, and countable union of sets of measure 0 is again a set of measure 0, and therefore we have that this theorem is this proposition is completely proved.